Hello, and welcome to this short video about auto configuration. My name is Jonas Johansson. I'm a solutions architect in the network programmability team at Cisco. This video is part of the Advanced Automation Principles series of talks about network programmability best practices. So what is auto configuration? Auto configuration happens when network devices automatically changes YANG model configuration data, either in response to some other configuration data being modified by a network manager, or when devices changes configuration data due to non-manager initiated configuration events, such as routing protocol updates or a technician inserting a line card which makes pre-configured network interfaces active. We call the former type of auto configuration side effects and the latter type system learned configuration. Side effects are common and often useful in management interfaces designed to be used by humans, such as CLIs and web interfaces, where they, for example, can be used to provide boilerplate configuration in order to save manual typing. However, this does not work as well with netconf and other programmatic interfaces. The reason for this is that service orchestrators and controllers expect to possess the single source of truth as far as device configuration goes. And when devices instead make up their own configuration, the manager will get out of sync with its devices. In general, the manager will not know that it is out of sync, and this can result in errors further down the line. As a general rule, side effects should be avoided for programmatic interfaces. If possible, only apply side effects when configuration changes are made from the CLI or the web interface, and require users of programmatic interfaces to explicitly set all configurations. In some cases, it's also possible to hide side effects from programmatic interfaces, but this requires that users can ignore the configuration in question. Require configurations to be given in canonical format. In the CLI caps example, this could be achieved with a pattern statement which enforce all caps in the string. When side effects are desired or necessary, it's better to use custom RPCs rather than edit config. The manager will of course still get out of sync, but at least it knows that it has done something unusual and can take actions to resync. The other source of routing configuration is system learned configuration. System learned configuration happens in devices which update YANG model configuration data in response to events not originating in a northbound manager. Examples include model routing configuration with manager configured routes as well as routes learned via routing protocols, pre-configured interfaces with some learned configuration, for example link speed, or when a line card is inserted to or removed from a chassis where operational state is auto-configured at runtime. So how do we deal with system-learned configuration? The general idea is to maintain system-learned configuration as operational state data, not configuration data. If the network management data store architecture isn't supported, this requires an operational state data models with mirrors the config model. This is complex and error-prone for a number of reasons. It requires duplication in the YANG model, resulting in redundant information. At the same time, not everything is duplicated, which means that the manager must merge the trees to get an overall view. And finally, this is only a modeling convention and can't be enforced, which means that network management can't depend on these parallel sets of information being present in all YANG data models. Still, before NMDA, this was the best we could do. NMDA, on the other hand, supports modeling system-learned configuration using the new operational data store. The operational data store contains all config true and config false data. Hence, retrieving from the operational data store can return conventional configuration data as well as configuration data learned from the system. Even better, devices can tag configuration data with an attribute indicating whether config data is regular config or system learned config. As a consequence of NMDA is that Yang data models no longer need to keep parallel sets of information, and as we can see in these snippets, which compares the pre and post MDA version of the IETF interface Yang models. People interested in more information about NSO and ConfD can find that on cisco.net. If anyone is interested in more information about the netconf and Yang automation testing program, it is available on the TLF Systems website. And finally, more videos in this series are available on our YouTube channel.